Okay, so many opportunities. How to get in? So I will share with you now what I consider to be the set of skills that is required from simulation engineers interested in working in this area. So those are the industry demands. Uh, so I will split this in basic, advanced, and specific skills. And let's start with the basic skills. So I start saying that, well, before you step into the world of numerical simulation, you should master strength of materials, material properties, so basic elementary theory. You should also have an excellent understanding of the finite element method. And I am saying this in a hierarchical modeling approach. So that means that you are able to uh, get a physical, real problem and idealize the problem with a minimum viable model. So that means uh, you start with a simple model that is already representative of the physical problem, and then you gradually add complexity to the model. So let's say you start with a 2D model, or you start with a beam model, then you move on to a shell model, then you may add contact, maybe you started with linear elasticity and then you add a more elaborate material model. So you start dealing with plasticity, for example. But what I mean here is really start with a simple model that will allow you to understand the problem gradually, and then gradually adding complexity to the model will lead you to very robust solutions. Okay, then next I mentioned about proficiency in at least one finite element pre and post processor, and also the solver. That's because, well, once you decide to step into more complex types of simulations, then you should not be struggling to prepare your model to generate the meshes and to visualize the results. And also you should have a good understanding of how your solver works, how to create things in that specific software. Then you can put all your attention to solve the more complicated problem that you are dealing with at the moment, instead of still learning the software. Before you move into explicit cell dynamics, you should have a good understanding and know how to interpret nonlinear analysis. So that means you understand all sources of nonlinearities, including geometric, material, contact, and eventually even following force. Because in explicit solid dynamics, you will probably be dealing with nonlinear problems, and most often with highly nonlinear problems. Scripting for automation, that's a good skill to have for any simulation engineer. It doesn't matter if you are going to do explicit solid dynamics or not, because, well, you can save time in pre and post processing mainly, but also, well, you can automate the submission of simulations and this type of thing. So that's a good skill to have. Then moving on to more advanced techniques that are more related to the world of explicit solid dynamics. Well, you need to understand dynamics, conservation properties, stress waves, and time integrators. So those are core concepts of explicit solid dynamics. And, well, before you start trying to do simulations in this area, you should understand what you're doing, right? So you should understand the underlying theories. Okay, the next thing in the list is understanding of advanced constitutive laws and data calibration. And I'm saying that because in explicit solid dynamics, you are probably not going to be using only linear elastic models. So a good understanding of some elastoplastic, viscoelasticity, viscoplasticity, and this type of models will help you to advance in this area. So being able to use some advanced discretization techniques other than the finite element method, such as the smoothed particle hydrodynamics method. So this is a meshless technique that may be useful when you are doing extreme large deformations where the mesh distortion would be a problem. Then you decide to use a meshless technique, or even to model fluids in a fluid structure interaction. So, and actually that's the next topic I put there. Once you move into explicit solid dynamics, you may be faced with problems that involve multi-physics. So fluid structure interaction is one of them, but also thermal coupling. So it's often the case that you are dealing with high speed impacts, high energy phenomena, where a lot of the energy is converted into thermal energy, okay? So you have the heating effects and this type of thing that should be considered in the simulation. Then advanced speed up modeling techniques and some familiarity with hardware specs, parallel computing, and HPC. So as your models get more and more complex, they will require more time to run. Okay, so being able to use some numerical techniques for speeding up the analysis without degrading the results is a very good skill to have. So there are things such as mass scaling, that's a very common technique in explicit solid dynamics, but also understanding the core concepts of parallel computing and high performance computing will only add positively to your capabilities of solving problems. Okay, so those are the basics and the advanced skills. And then if we think about specific skills, then here I'm talking about industry-specific skills. So let's say you're interested is to perform crash test analysis of standard passenger vehicles. So you may need to become familiar with the regulations and standards in that specific area. So there are some examples that are listed here, such as the Euro NCAP or IIHS, this type of thing. Or even more specifically, if you are involved with a particular product, you may have standards or guidelines for simulating that specific product. So these are more abstract at the moment, and I'm sure you will identify what are your objectives, and then once you do that, you need to keep in mind that you should be researching what are the specific learnings that you should pursue for that specific area. Another thing that I put in this specific list is some programming skills, because it may be the case that you will be working with in-house codes, and then you will not be only an end user, but sometimes you need to interact with the source code. That may be especially true if you move into the military sector, where there is a huge amount of in-house codes. Okay, and then finally, so everything that I said here is very technical, but don't forget that as an engineer, especially as an engineer working with other people, you also need to develop a set of human or soft skills. So one of those skills that I consider one of the most important is writing and documenting of your work. So as a simulation engineer, you should be able to present uh, details about your models in written format. Okay, so preparing reports so that other people can understand what you did and eventually even to reproduce what you did. And not only written communication, but also delivering technical presentations and then considering mixed audiences. So there will be many cases where you will be presenting to other engineers, but there will be many other cases where you will be presenting to people that don't understand computational simulation. And you need to be able to deliver the presentation in such a way that non-experts will understand what you're talking about, so that they will get to the same conclusions that you got when you performed your simulation, and will understand the value of what you are telling them. Okay, so the next one here is very related to writing and delivering presentations, because this is still about communication. So having the ability to interact with different departments such as testing, materials, manufacturing, so having a good understanding of all those areas that are either providing inputs to your simulations or using the outputs that you generate. So having a good relationship with those other departments will always be beneficial for both parts. Good time management and planning. So that's pretty obvious in, I think, in any area. So no need to talk much about that. Okay, then problem solving skills and troubleshooting. So the world of computational simulation is very challenging, and there will be many occasions where the results are not what you expected, or the model doesn't work, uh, the simulation fails for unexpected reasons, and then you need to investigate and find the reasons. So having a strong background in the underlying theory and understanding the software will be very helpful. But yeah, you must have this ability to investigate problems and find solutions.